In this problem, we want to determine open intervals in which graph of the function is concave upward or concave downward. So we've got f of x is equal to x plus 3 over x minus 2. I want to use a quotient rule. Top part will be p and the bottom part will be q. We need p prime. The derivative of x plus 3 is 1, and we also need q prime. The derivative of x minus 2 is 1. Now our quotient rule is p prime q minus p q prime all over q squared. So for our first derivative, p prime is 1 times q, which is x minus 2, minus p, which is x plus 3, times q prime, which is 1, all over q squared, which is x minus 2 squared. Now those ones aren't doing anything, so I can drop them. So I got x minus 2. Remember, you have a negative out in front of your parentheses, flips the sign of everything inside. So the x becomes a negative x, the positive 3 becomes a negative 3, all over x minus 2 squared. Now x minus x drops away. Negative 2, negative 3 is negative 5 over x minus 2 squared. And that's our first derivative. Well, we need to find our second derivative. Different ways you could do this. You could do the quotient rule again, or you could take that x minus 2 squared and move it up on top with the negative 5, and it becomes x minus 2 to the negative 2. So then for our second derivative, the negative 5 stays out in front. Here we got parentheses to a power. This is a chain rule, the general power rule. It says you take your power, put it out in front. So put negative 2 out in front. What's inside the parentheses remains as is. Lower your power by 1. And then you multiply it times the derivative of what's inside the parentheses. Well, negative 5 times negative 2 is a positive 10. X minus 2, negative 1 is negative 3. The derivative of x minus 2 is 1. So we're going to take that x minus 2 to the negative 3, move it back down to the denominator. So we'll have 10 over x minus 2 to the positive 3. And that's our second derivative. Well, we need to find our critical values. So we set our top part equal to 0, and we set our bottom part equal to 0. Now 10 is equal to 0. There's no variable to solve for there, so we don't need to worry about that side. Over here, remember, if you have parentheses to a power equal to 0, you can drop your power. Just set what's inside the parentheses equal to 0. So that gives us x minus 2 is equal to 0, which then gives us x is equal to 2. So that's our only critical value. Clear over here is negative infinity. Clear over here is positive infinity. We want to pick test cases. I want to choose something between negative infinity and 2, like 0. Something greater than 2, like 3 or 4 or something like that. Let's choose 4. Now we want to plug those into our second derivative. Now these I could probably eyeball and see. If you need to, plug it in your calculator and do it that way. Now if I look at the number up on top, 10, that's always positive, so we can ignore that. If you got part of your function that's positive, you can ignore that part. This part down here, 0, we're going to put 0 in for x. 0 minus 2 is negative 2. Negative 2 to the third power is negative, which means this is concave down. If I put 4 in there, 4 minus 2 is 2. 2 to the third power is positive, so this is concave up. Again, all we care about is the sign. So our answer is going to be concave down from negative infinity to 2. And then it's going to be concave up from 2 to positive infinity. Now realize my graph doesn't exist at 2. If I put 2 in for my for x, my denominator, 2 minus 2 is 0, so that's undefined. But these are open intervals, which means it doesn't include 2, so we're fine there. And these are our answers.